Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard.
In this video, we're going to be determining the element stresses for 2D solids. So we've already discussed that the stress in a solid is going to be equal to the constitutive matrix multiplied by the vector of strains. And then, of course, once we do our finite element discretization, our strains are going to be a function of that B matrix, which has all of our shape functions in it, multiplied by our vector of displacements. So this first equation is just generally true, and this second equation is true on each element. So we need to find the strains element by element, and then we can use those strains in order to find the stresses. And just as a reminder, what this looks like is our 3x1 stress vector with our two normal stresses and our shear stress, which is going to be equal to that constitutive matrix, which is different for plane stress or plane strain. And then that is multiplied by this B matrix, which has those derivatives of psi1 with respect to x, of psi1 with respect to y, and then with respect to y again, and then with respect to x again. And so this pattern is repeated for each shape function, and of course we could have any number of shape functions depending on the element type that we have. And then finally, that's going to be multiplied by u1, v1, all the way down to un, vn. So the idea here is that after we have solved, we know all of the displacements for each element. And so we can use that along with this B matrix and D matrix in order to find the stresses for each element. Now, these stresses by themselves are not typically useful for determining failure of an element. So in order to look at that, we're going to first look at something called the principal stresses. And there are going to be three of these. So sigma 1 is typically the maximum normal stress that we could have. And what I mean by that is we typically think of things in purely the x, y direction, right? This little element that we have in purely x and y. And so with that element, we have a sigma x pulling like so, a sigma y pulling in the y direction, and then we have our tau xy, which is pulling along these surfaces. So the idea is, instead of finding an element that's perfectly oriented with x and y, we can rotate this element. And as we rotate, we find that these sigmas change values. And instead of being that original sigma x and sigma y, we'll have a variety of elements. And this shear stress will also change. Well, if we get to a very specific location, so if we're able to rotate this to something called the principal axes, then the tau xy actually goes away completely. There's no shear stresses. And we're just left with the normal stresses, sigma 1 and sigma 2, which are called the principal stresses. So the equation for these is just sigma x plus sigma y over 2 plus the square root of sigma x minus sigma y squared over 2 plus tau xy squared. And then sigma 2 looks almost exactly the same, except we are going to subtract off that square root term. And then sigma 3 could be one of two things. If we're looking at plane stress, then it's just going to be identically zero, because that's what plane stress means, is that there's no stress in a third direction. And when I'm talking about sigma 3 here, I'm actually talking about the stress in and out of the page. And so with plane stress, we just don't have any sigma in the z direction. And then looking at sigma 3 for plane strain, it ends up being nu times e over 1 plus nu 1 minus 2 nu, and it's actually going to be multiplied by epsilon x plus epsilon y. And that's just a little bit easier than figuring that out based off of these other stresses. And that was for plane strain. So in plane strain, the strain in this third direction is equal to 0. So it's always the same thickness. So that means that there is some stress associated with it. Now, these three principal stresses are still not perfect for determining failure of a material. And so we go one step further and we calculate something called the von Mises stress. And this is equal to 1 over the square root of 2 multiplied by the square root of this sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared. And so we're looking at these differences between the principal stresses, taking the square root of the sum of the squares of those differences, and that is this von Mises stress. And again, this is useful for determining failure. Now, let's start thinking about some of the elements that we might be using this for. So the first element that we've already talked about is the constant strain triangle. And that triangle just has 3 nodes. And the idea here is that we have constant strain, right? And so if we have constant strain, that also means we have constant stress, which means that if we can figure out what the stress is on any point of this triangle, then we found it for the entire triangle. Now, there are other elements that we might be interested in. One of those is a linear strain triangle. So for a linear strain triangle, we just add a couple more nodes. And again, if we have linear strain or linearly varying strain, that means that we also have linearly varying stress. So just like when we were looking at the stresses on a 1D element, whenever we have linear stress, we need to look at all of the extreme values. For the linear stress element, we actually need to go find the stress at each of these 3 nodes and find the maximum of those. And again, this is because with linear strain, we're going to have some variation in our B matrix with position. And so we need to use the positions 1, 2, and 3, which are the maximum values there, in order to figure out how that strain changes on those elements. Another element type that we might use is the bilinear quadratic element. This is very similar to the linear strain triangle that we just talked about. We have linear stress. And so again, we need to find the maximum stress from those nodal values. Now, it is of course possible to have more complicated elements, and so we could have quadratic stress as well. But the second we step into that realm, then it gets a lot more difficult. We need to find the maximum over the entire element instead of just looking at the nodal values. And so we're not going to get into that today. But in short, the procedure is we calculate our B matrix, multiply that with our D matrix, and then perform this matrix vector multiplication to find our stresses. Then once we have those stresses, we can find the principal stresses and the von Mises stress. And this von Mises stress is what we actually care about. So this is the big thing. And then if we're doing that for constant, we just need to do that once because this B matrix doesn't change. But for linear stress, that B matrix does change in space, and so we need to find it at all of our nodes. All right, that is all for this time. I hope this was informative, and I will catch you in the next video.